Hi, in this example, I'd like to show a more complex control. In this case, I will use pysimCoder, NUTTX, and the CAN bus to control an educational plant that we have in our laboratory. This is the plant. We have two disks, and each disk is connected to a motor. And between the two disks we have a spring. We can move both disks only using one of the two motors because we have a direct connection between the two disks. In this case, we want to use the motor on the left to move both disks. And in particular, students have to control the position of the disk on the right using the motor on the left. And the movement of the left motor passes through the spring to the second disk. The left motor is controlled in torque mode, and we can measure both the angles of the two disks using the motor encoders. This is the board that we use to control our system. This is a Nucleo board, and we have a transceiver to allow to have the CAN bus connected to this board. The Nucleo is a F746ZG board from ST, and we use a CAN transceiver of micro A. And this is a CAN transceiver based on the MBC2551. And this transceiver is connected to the TX and the RX pins of the board and are connected to the CAN1 of my device. The model is based on the following parameters that we have previously identified. We have the spring constant, the different damping constant of the spring and of the two motors, the two inertia of the motors, and the torque of the motor 1 is used as control signal, and in particular we can control our system using the current that we give to the first motor. And both motors have incremental encoders to get the position of the two disks. The plant is a little complex because it has 2 degrees of freedom, and we have to build 2 differential equations, one for the position of the first disk and one for the position of the second disk. And we have a 4th order system. Using these states variables, x1 equal angle 1, x2 equal angle 2, and x3 equal the speed of disk 1, and x4 equal the speed of disk 2, and the current E1 as input, we can obtain the following state space matrices A, B, C, and D. And we have at the end a system with input E1 and output angle of disk 2. The controller design is performed using a Python script, and in particular we use the Python control package and additional function developed at the SUBSI. We will implement a discrete state space controller, and we have to place 5 poles because we introduce an integrator in our controller to avoid finite state errors. The 2 angles are measured, and we can use a reduced order observer to get the two angular speeds of the disks. The controller is finally implemented in a compact form, where in a single LTI block we have the observer, the controller feedbacks, and the integral part. And we introduce an anti-wind-up mechanism. These are the controller poles. We have a bandwidth of 10 radians per second, and we can see where we placed our 5 poles. The next step is to implement the controller using pysimCoder. I start pysimCoder on my PC, and I open my standard controller as a starting point to implement the new controller. Copy and paste. This is a standard controller which implements an anti-wind-up mechanism, and now I can fill it with my special blocks. First of all, the system uses as input the reference signal and the two measurement of the two angles of the disks. This means that this blocks has 3 inputs. Okay. Now we can get first of all my input signal, which is a square generator, and I have an amplitude of 1, this means 1 radians, and I give a period of 10 seconds and a half period of 5 seconds. This means that my reference signal will change between 0 and 1 each 5 seconds. Then I can get from my Maxon system, I can get the 2 Maxon encoders that are used to measure the 2 angles. The first one, he is connected to CAN 0, has a device ID of 01, and has 500 pulse per turn. And the second has the same CAN device, has an ID of 2 and a resolution of 500 impulses. Okay, I need a system to monitor my signals, and I put all my signals now here. To the serial out, which send the measured signals and the input to my PC, and I need the motor to send the calculated current to my first motor. And here I have to change some parameters. Is CAN 0, and here I have the 2 internal gains of the Maxon driver. Now the system is ready. I have to choose my template makefile NUTTX, and my parameter scripts which calculate the controller parameters. I save this plant. And now I can generate my code. It's done. The next step is to flash the generated code into my board with this little utility. And I can enter my card, and I have my main application that starts my executable. I start the executable, and I start my monitor function. Three inputs, and I can start the server. I can try to disturb my system and see how my controller responds to my disturbance.